Go. Okay, thank you for being here. My talk is about complex cameras, which are complex. We know that. And my name is Jacopo. I'm an embedded Linux engineer. I mostly work on cameras and multimedia devices in general. I mostly work for Renesas. I'm a consultant, so my time bounces between different things. And these are my emails and IRC contacts, so feel free to get in contact with me. Motivation of this talk is that the complexity of capturing images we are used to in embedded systems is arriving to consumer devices like laptops. And the question is Linux ready for that? And the answer is, of course, no, it's not. Otherwise, I won't be giving this talk otherwise. And this is the outline of the presentation. I'm going to very briefly talk about why acquiring images is complex and the solution that Linux provides for dealing with complex cameras, which is the media controller, and the problems related to media controller. And finally, I would like to present you a possible solution to the said problems, which is called Lib Camera, which is currently in development. So let's start talking about image capture and pointing out that capturing images, it's basically a sequence of processing blocks that deal with the digital signals. And the complexity spans from the application processor, which is usually an SoC, to external components like sensors. And in order to give a presentation of said complexity, I would like to start from the very beginning of the acquisition process, which is the sensor itself. And the sensor, an image sensor, is nothing but a grid of photo-optic receivers, which are called pixels usually, which filters applied up top. So each pixels filter lights and transport a single color information, which said colors being red, green, and blue, because the human eyes is most sensible to those frequencies. And the way we dispose filter is called the Bayesian pattern. The Bayesian pattern is what is usually called the raw image, and it's usually very big, and it's usually in a format which makes sense just to the producer of the sensor itself. Knowing that each single pixel transports a single color information, we do have a problem. That it's how do we reconstruct the full color of each single pixels, and we do that by doing what is called demosaicing or debayering, which is a kind of a complex interpolation problem, because we use the colors from neighbor pixels to reconstruct the full color of each single pixels. And this process has to be done in different steps for all the pixels in the sensor, which are usually a lot. So that's a tough computation. And that's a problem that starts from the very beginning of the image acquisition. And after we do that, after we reconstruct the full color of each pixel, we do have another problem, which is translating those digital information in a color space, which is a mathematical model to represent a correlation between lights and the perception of colors, which is standard, so that we can transport images back and forth with other systems. Well-known color spaces are sRGB, Adobe RGB, CYMK for printers. And to do that, we have to do other computations. Even though we end up with an image, which is the raw image, in a known color space, which is very big. Raw images are huge. If you want to transport them back and forth from your sensor to your SoC, that's a lot of data. So a common way to deal with that is performing some kind of pixel encoding and encode the pixel in a format which is easier to transport back and forth, like RGB 566, RGB 666, some permutation of YU, YV, and that's even more computation. So just for transporting images, we have done a lot of calculation already. So, and maybe we also want to do some more advanced feature like 3A, which is the autofocus, auto exposure, auto white balancing. We want to do pixel correction. We want to do enhancement of pictures, defect cancellation. That's even more computation. And this time, they do not depend on the format, which is configured on the sensor. They do depend on the application. And your application might be very different. Your application might be an FPGA block processing images. Your application might be the camera application you have on a smartphone. And that creates a feedback loop from the acquired images that get transformed, get sent to the SoC, provides them to the application. The application said, I want this image a little bit more exposed. Tell that to the SoC, and the SoC instructs the sensor to give us an image which is slightly different from the previous one. So that's a feedback loop, and that imposes latencies, which have to be very low in order for this process to work effectively. So to sum up, digital imaging is computationally expensive. It has big requirements in terms of memory, in terms of latency. It's a complex problem. So we have a complex platform to deal with that. The complexity is, again, from the very beginning, from the debayering and the demosaicing, pixel encoding. We have complexity for tuning the image quality. We are used to images which are very high quality on our smartphones. That's a lot of work. And there is a strict correlation with the application providing feedback to the tuning machine. And the images are huge. We work with an image which is already pixel encoded in 1080p, which is not a huge resolution. It's more than 4 megabytes of data. So we're moving a lot of data between the sensor and the system memory. That's another problem we have to deal with. If we look at the architecture of a modern system that captures images, or a modern SoC, we do have very fast CPUs nowadays. We run with CPUs in the order of with speeds in the order of the gigahertz. And we do have a lot of system memory also. We do have very powerful ISPs, which are system peripherals that works on digital signals like images. And we do have very large bus interconnection to transport images back and forth. Externally, we do have a sensor that provides the raw data or the encoded data. But 10 years ago, before the smartphones era, so let's say 2005, something like that, embedded systems were very different from what we have today. They were, of course, much less powerful. They were 100 of megahertz of clock frequency and 100 of megahertz of system memory, maybe. They were much more proprietary, because if you were to design an embedded product 10 years ago, you had to tailor all single components of the system for your very specific application case. You didn't have anything like an Android BSP at the time. You won't receive a Linux kernel with support for your platform at the time. You have to tailor every single component. And so that resulted in much less standardized systems. So lot of tuning that you have to do on your platform to have your system working properly. So around 10 years ago, it was very popular, the idea of having the sensor doing most of the computations. So the sensor provides you images which are already encoded, already enhanced, with 3A already performed. And your SoC basically skips the ISP completely, if there was any ISP at the time, and just act like a DMA engine and transfer raw images without touching them, without modifying them, directly to system memory and presenting them to the user. So, but if the sensor does all the computation, that means that the sensor is very complicated. It's a very complex sensor. And the very complex sensors means that you have to write very complex driver to deal with that. And since the sensor is not part of your SoC, the silicon vendor won't provide any driver for the sensor you're using, or at least it would be a very basic driver for that. So if you want to implement that, it's time, money, and effort if you want to use that for your product. Also, complex sensor architectures means they are expensive. And if you care about your bill of materials, and you do care about your bill of materials, complex components means expensive components, and that's not good. Also, since we are running mostly on battery-powered devices nowadays, complex sensor means that they are power-hungry, and you have to be very careful in how you power up and down them in order to be efficient. More in general, if you put more computing block on the sensor itself, that means that you have less space, and space could be money, time, effort, or physical space on the sensor itself for doing what a sensor should do, which is providing picture in high quality. But nowadays, we run on embedded systems which are very complex, and they have very powerful ISPs. ISPs, as I've said, it's an image signal processor, which is basically a system peripheral that operates on digital signals. It does all the computation that we have seen at the beginning of the presentation. It is composed by processing blocks, which can be linked one to the other in order to perform computation. And each blocks can do things like transferring data to and from system memory, manipulate the images, perform enhancement or conversion between formats. It's everything we have seen at the beginning of the platform. The design of the ISPs, though, it's very system specific. Depends on the use case for that your SoC targets. So if you have an SoC that targets the automotive market, you maybe want to have a lot of DMA interconnections because you want to transfer a lot of data to different processing blocks. If your ISP is designed for an SoC that targets mobile phones, you want to have an ISP that provides images in different formats because it's easier to present them to the user if they want to take a picture. So you want maybe the JPEG encoding image provided by your ISP. So the ISP design and the ISP handling, it's really platform depending, and each SoC has different ISPs. Also, the ISP is a system peripheral, is on the system on chip itself, so it's very fast interconnection with the CPUs and very fast frequency. It operates at very fast frequencies. It interfaces directly with a lot of system peripherals, like the DRM for displays, if you want to capture and display images automatically without going through the CPU. It interfaces with GPUs. Sometimes you see a system that uses the GPU for doing the JPEG encoding of images. That's a computational problem. That's a combinatorial problem. So that fits very well for GPUs. You might want to have codecs. You want to capture image, and you want to make a video out of that. If the ISP is on the same system on chip, it's very easy to move data between the ISP and the codec if you have any of your systems. Also, it comes with your SoC. It's not something that you pay more money for, more than what you already pay for your system on chip. And vendors are competing on that because they are trying to differentiate between the use case for the SoC, also like they do for GPUs nowadays. So yeah, we really want to use ISPs because we have them. We have a lot of computational power in our system on chips, and making a sensor doing the computation doesn't really make sense nowadays. Not anymore, at least. That's something like a personal thing. Like 4 or 5 years ago, we've seen a lot of vendors trying to move in the ISPs out of the system on chip itself. Maybe you have worked with Ducati, Da Vinci from TI. I'm sure that other producers are doing the same. They provide you tiny microprocessor where you could write your driver for the camera for an RTOS that runs on microcontroller and has a very complex RPC system that talks with your application processor. And why would you do that? I think that sometimes vendors are not that happy to write drivers for GPL kernel. And they feel like if they do that, somebody may claim for the code to be given back. So I think 4 or 5 years ago, producers have been doing that to provide a safe space for people that doesn't feel comfortable to writing driver for a GPL kernel. To do that in a tiny space in a microcontroller where nobody will ask you for anything to be given back. They claim that it was done for performances reason, but I don't know. So I wonder if that's still a thing. There have been systems like 5 years ago in production for that. I'm not aware if there are any more in this day, probably for very specific applications. So we do have a problem though on the software side, because the Video for Linux, which is the Linux kernel framework for dealing with cameras and multimedia devices in general, has been designed in a time where your system was nothing more but just a DMA engine. It got images from your sensor and transferred them to the system memory. And for this reason, the only entry point we had for that was a simple device node in user space. You use the Video for Linux 2 API to configure the whole capture infrastructure, and you just start streaming, and the image you receive from the sensor gets written to the system memory, and that's it. You cannot do much transformation here. You maybe have a scaler, you maybe have a format converter, but that's very simple devices. And Video for Linux has been designed at a time when this was the system we were dealing with. That was like 10 years or even 15 years ago. But 6 years ago, that was from Nokia people. They were trying to do a Linux phone at the time. We all know that it didn't go well. They got bought by Microsoft. The Linux phone division has been killed, but they given back to the community a thing that is called the media controller. The media controller, it's an extension to the V4L2 API and to the V4L2 model of exposing devices to user space. And the media controller allows your driver to expose every processing block that you have on your ISP as a sub-device in user space. So we move from the model when you have a single entry point for your application, which is that video 0, to a model where you have a lot of sub-devices, each one representing a single block of your ISP, and still a device node for transferring images back and forth to the memory. The media controller also introduced what is called the media graph. So you got a new device, which is called that media 0, media 1, media 2, whatever, that allows you to configure the linking and configuration of each sub-device in the pipeline of the image acquisition. So that's more complexity. And it got to mail like 7 years ago, something like that. And we still miss support for that in user space. So the media controller is very nice, but in order to use that, you have to go for and do linking on each sub-device. So you got the new IOCTL, you open your sub-device, you link that with its next sub-device, and you program a pipeline in that way. Also, you have to configure the formats on each sub-device properly in order to have each processing blocks talk with the same format to his next one. Also, you got the new set of IOCTL, which is the video C subdev IOCTL, or you can use the media CTL tool for doing that, which is a wonderful syntax like this one, which is very clear, and it's very easy to adapt to every use cases. Of course, it's not. So dealing with the media controller is complicated because the system boots in a way that is not usable. The system boots, and you cannot capture images. You have to go and do the configuration of the whole pipeline, and sometimes we have 20 sub-devices. So that requires for the application to, maybe an application was just to capture images, but if you are writing an application for a system that runs on media controller, and nowadays all mainland driver, the Video for Linux drivers runs on media controller, the application should know a lot of details on the hardware platform. That's not good, because that means that it's hard to port the application from one platform to another. Also, before triggering a capture operation, you need to go and configure precisely the pipeline, knowing which formats apply to which block, knowing that maybe some blocks have limitation on the pixel format they accept. So you get to read the data sheet. And if you're writing drivers, that's fine. If you're writing application, that's not good. That's why after 7 years, the adoption of media controller in BSPs or in embedded products, it's not that. It's not the one that we were expecting. Let's put it this way. So as I've said, this is acceptable for embedded systems. Embedded systems has a very specific user space. So if you bake a few scripts that configures your system at boot time for setting up the pipeline, that's fine. You bake that in your rootfs, you put that in your embedded product, That's not a big deal. It's a deal, but not a big one. Is that acceptable for a laptop? Is that acceptable for a regular Linux distribution? Is that acceptable for consumer devices? It's not really, because if you install Debian, Debian doesn't know which system it runs. So Debian doesn't have to bake a lot of different scripts to run at boot time, to configure the pipeline in order to make a Skype phone call. That's not good. So until today, that was not a real problem, because in laptops and desktop, well, desktop have other kinds of connection, but mostly in laptops, on x86 laptops, all the cameras were USB. So you got connection to the USB bus, and they are very smart devices, because they are not just smart devices in the way that we have presented smart devices. They also talk USB. So it's very easy to configure them. You just use the UVC, that's USB video class control protocol, and you configure the sensor using that. The sensor gives you back frame on USB packets, and you just need to move that to your system memory. That fits very well in the single device node approach that VIDA for Linux had so far. And it's totally platform agnostic solution. You have USB, your camera works. We do have a problem, though, that USB is not efficient as using an ISP, and USB is expensive. USB, you maybe have limitation of ports, and you have an ISP, and you want to use that. And recently, we have seen Intel shipping processor, very well-known one, like Kaby Lake and some Skylake platforms, which have a very powerful ISP. And Intel is doing the right thing. Intel is submitting patches for said ISP, and the patches are on Linux Media. They probably will land in 4.21 or something. So we do have an ISP on a system that is a laptop. So we have a problem. And just to give an idea of how complicated an ISP might be, that's how the IPU3 works. IPU3 is not even the most recent one. They do have IPU4, but there is no driver, no public driver for that right now. So that's the simplified version of the IPU3. IPU3 is composed by two media graphs, one that takes care of capturing images and the other one that takes care of transforming that in order to be presentable to user space. The ISP is fed with raw images, and the raw images get captured and transformed in some sort of Intel-specific raw format. And that format, which is not expectable by user spaces, if not with very specific tools, gets fed to the input of the imaging unit. The imaging unit processes the raw image and gives you back three different outputs. One, which is a scaled output for the viewfinder. If you are if you're writing an application, you want to do the viewfinder mode, you want images to be small and very fast to process. So the viewfinder outputs give you a scaled down image in order to be used for the viewfinder mode. You also have an output node, which gives you back a converted in YUV format full-size resolution, and that's what you use when you capture an image. You won't use the small one, you use the big one. And those two are given you back at the same time. So the IMGU is doing a lot of things. Also, you got the statistic node. So you got metadata information on the image you captures. And you may ask why, because that goes into a 3.8 tuning machine, which is a very complicated software machinery, which is Intel proprietary, that runs in user space, that chunks all the metadata and transform them in parameters that configure the IMGU. So that's the feedback loop we have seen. You got metadata, they get processed by this very complex and proprietary stuff, get written down to the parameters input node, and that changes the way that images are transformed at the next capture. So this is a simplified view. It's a simplified view because you have 4 of this, not 2. And you can handle I think 2 or 4 parallel capture sessions at the same time, and you got something like 20 sub-devices in the user space. So that's a very complex device. That's a very complex ISP. And we do have that in laptops. nowadays on the market. And that's an email that was on Linux Media. That's from last April, I guess. And there was a bug report that the webcam doesn't work on these specific laptops. And the answer is it's cold stone. Like, you need drivers for that they are coming. You will have that. But anyway, that's a complex camera. That's a complex camera, and you need special user space to use that. As of now, there is no plan to support this in user space. That's very bad. That's very bad because that means that for these laptops or other laptops or Chromebooks that will use this processor, the camera would never work with Linux. So that's a very bad thing. I probably use the wrong order of slides. That's very bad because Linux distribution won't support cameras on those platforms. And vendors that have been using vendor-specific solution like Android or Chrome OS will keep using their own very specific solution. They won't contribute back to the community in any way. So maybe you have a Chromebook. Chrome will work with the camera. Linux does not. So that's very bad. Although there is maybe hope for that because there might be a solution for this problem. And the solution is called Lib Camera. Lib Camera is a very recent project where the Vida for Linux community has joined forces with the industry because industry and vendors are very aware of the problem that Linux won't work with cameras on their product, and that's very bad. So Lib Camera as a website, of course, Lib Camera is a user space stack, which is the humble purpose of being a complete software stack for cameras on Linux. That sounds as a very scary thing. It aims to be compatible with existing V4L2 application, with existing V4L2 compatible frameworks like GStreamer. It aims to be compatible with Android and Chrome OS. And it's very interesting how Android deals with camera. That's totally different topic. And it's, of course, free software. It has an open development. It's open development. There is a mailing list. There is a patchwork. There are patches flying around on the mailing list. But it also provides a safe space for vendors to keep their IP or what they perceive as intellectual property valuable things in a safe space. Because today vendors are competing on image quality. That basically means they are competing on 3A algorithm and optimization of the image quality. Lib Camera have to give them a free space, for a safe space for do that, because otherwise they will keep using proprietary solution like they are doing nowadays. That's a very simplified picture of how Lib Camera might look like, an architecture that uses Lib Camera. So starting from the very top of the image, you got native Vida for Linux 2 application, frameworks like GStreamer, hopefully in the future native Lib Camera application or Android on the side. And they all will talk with the middleware, which is Lib Camera, that will take care of dealing with media devices and Vida for L2 sub-devices and devices on behalf for your application. Going in detail on what Lib Camera would look like, Lib Camera will have a public API, and the public API will expose simple camera devices. You will be abstracted away from the complexity of dealing with video device node 1, 2, or 3, or configuring the media controller. And the Lib Camera will have a platform agnostic part, which aims to be the same for all the platform Lib Camera will run on, and the device-specific part, which is the pipeline manager. The pipeline manager is the part that interfaces with the media controller, set up links, set up formats, do the calculation which format are opportune for your sub-devices. And that part will be very platform specific. We have started working with the IPU3. We probably will tackle Rockchip after that. There are a few devices and a few producers which are interested in doing that. And this part is the part that abstracts away all the pain that you have nowadays to work with very complex ISPs on embedded systems. Also, there will be this tiny part here, which is not a component of Lib Camera, but is the idea of sandboxing. So running in separate process with an RPC systems, what vendors today use for configuring the 3A algorithm of these systems. So this part will not be linked to Lib Camera. Lib Camera will be, it's C++. It will be LGPL as a license. But the thing that vendors write should be kept separate from the processing, from the process that runs Lib Camera. So this part will be run in a separate thread, sandboxed, and with an RPC system in place for talk with external components. Of course, there will be a lot of helpers that help you deal with Vida for Linux and your platform specificity, and that will be part of the library itself. So Lib Camera, it's a very early stage of development. It has a lot of more documentation than code actually right now, and not all the documentation is on the website, but it will get there. And there is an official Git repository which is hosted by Linux TV, which is the entity that hosts Vida for Linux basically. And that will be the official repository. Well, all the code will be. There is a mailing list you can find on the website where patches are already flying back and forth. And of course, there is an IRC channel where you can get to and talk with developers. Of course, the input we have are just from a few producers and from a few use cases. So we really want to talk with anybody working with cameras because we need more input for knowing different use cases we're maybe not thinking of at the moment. And since right now we are in designing phase, that's the right time to get to the Lib Camera IRC channel and talk with developers and maybe point out that you have a different use case from the one that Lib Camera has been designed for so far. Also, if you want to know more about the complex cameras and Lib cameras, there are a few talks which it's a debated talk. It's a debated topic. And just at the most recent Embedded Linux conference, there have been 2 presentations about that. One, it's specific on Lib Camera. The other one, it's more generically on how Vida for Linux is dealing with complexity in the last years. And there are notes for the meeting that was the kickstarting of the Lib Camera project last June in Tokyo, and there are information about the designing process, and so I invite you to have a look at those pointers. So basically, that's all for me. I think I might be on time as well, and I really hope you have questions. Don't be shy.
So, come on. Okay.
In a complex video pipeline, there are different ways that the same thing can be done, like resizing can be done in the sensor or in the ISP or other blocks with different levels of quality. So how do you think Lib Camera will go in being able to expose the possibilities and exploit them in a portable way to applications?
Well, if you're talking about the hardware-specific part, which is the pipeline manager, that will expose just a few use cases. The internal API reasons in terms of frame format and frame sizes. So the way that the pipeline manager configures the pipeline for doing that, it's up to the implementation. We hope to have to distribute a library with several pipeline handlers, each one running on a specific processor and each one with a specific implementation. So the pipeline manager will receive like a request, I want an image in YUV or JPEG at 1080p resolution, and the pipeline manager has to find out, it has to be implemented, how to get that from the pipeline that you have. That's up to the implementation of the pipeline manager, and that's up to the platform itself. So that's a detail that, by the way, that will be completely abstracted away from the application, because the application won't need to care about the pipeline configuration at all. Just reason in terms of, I want the front camera to capture images at this resolution. And the implementation would hopefully deal with that behind the back of the application.
Okay, other questions? Anyone? Okay, so thanks, Jacopo.
Early lunch.
Early lunch.
Even better.
Thank you very much.
Thank you.